a fourth-year course called Current Interpretations of Quantum Mechanics, and he'll be giving a talk on what is science about.
Okay. Okay, well, thanks very much for the invitation. As was mentioned, I'm a professor in the physics department. I'm a theorist. I work mostly on quantum optics and condensed matter physics. So I'm going to be talking mostly about physics when I talk about what science is about, because that's the business I'm in. And I want to mention that at least my first experience in thinking, having some idea of what physics is about was, working through free body diagrams. Okay? I seem to have spent an immense amount of my life as a young person doing free body diagrams, drawing tension forces and gravity forces and the normal force on the block, which always puzzled me. I never quite understood that and so on. Working through all these things, okay? And then later on, I learned a little bit more. I learned a bit about electromagnetic fields, okay? Maxwell's theory for the electromagnetic field. So at each point in space, one would associate an electric field and a magnetic field. And yeah, as these oscillated, they were responsible for the colors we see, and they exerted forces on charged particles. So this sort of collection, this sort of picture was certainly my first impression of what science is about. But implicit in this is the sort of idea that it's about the furniture of the world. Right? We're talking about what's there. Okay? And I'm going to call that perspective realism. As Patrick mentioned, realism, realist, this word can have many uses. I'm going to use it to mean that the idea that science is about physical objects and their changing attributes, not necessarily that what it says about them is correct or anything like that, but just that the science talk is about that. Okay? That's how we should understand what science talk is. Now, when you start to do quantum mechanics, you immediately have problems with this. Okay? And let me just give you a little toy example. These are bilayer materials that are very interesting these days because their band structure actually has very interesting topological properties. Okay, this is molybdenum disulfide. But the only important point for this talk is that it's sort of a 2D material, and I want to imagine that I add an electron to it. People can do these experiments. Okay? And when I do that, I describe the electron by a wave function. Okay? Some of you have seen a lot of this, some maybe not so much, but there's a wave function that I write down. It depends on space and time. And when I plunk an electron down there, the wave function sort of spreads out, much in the way that a water wave does if you throw a rock in the pond. Okay, so it maybe starts like this, and it spreads out, and spreads out a bit more, 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 and then maybe you decide to look for the electron. You do a position measurement of the electron, and yeah, maybe you find that it's there. Okay. Now you do exactly the same experiment again. You put the electron down, and I'll skip all the intermediate steps. It goes to this point. You do another position measurement, and well, here, maybe you find the electron is there. Then if you do the experiment again, maybe you find the electron is there. Okay. And all our theory does, all quantum mechanics does, is predict probabilities. It's going to predict where you're likely, most likely, or less likely to find the electron. In fact, the square of that wave function gives you that probability. Now you can ask, well, now what happens after the detection? Well, it turns out that after the detection, the wave function that you associate with the electron is sort of where you found the electron. That's not so surprising, but there's sort of a collapse of the original wave function that you had, and now you got to start with a new wave function. And that process is not described by Schrödinger's equation. You need a new rule you have to add that describes that collapse. Okay. And that's a bit strange because, of course, well, originally, before you did the collapse, the wave function was everywhere. You measured, then collapse it. How did it get from here? It went to zero, or did it all come down here, or did it do it instantaneously? It seems as if this wave function here is some sort of artificial structure that you shouldn't really associate with nature. Now, this is not the first time that these kind of artificial structures appeared. Okay? If you go back to Newton, okay, he introduced the idea of absolute time, right? Absolute, true, and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. Well, how does one understand that? Certain people thought it was just unintelligible. It made no sense to talk like that, okay? One of them was Ernst Mach, okay, who wrote, "This absolute time can be measured by comparison with no motion. It has therefore neither a practical nor a scientific value, and no one is justified in saying that he knows aught about it. It is an idle metaphysical conception." So the idea that Mach put forward is that what our science is really about is our sensations, or directly observable objects, things we can sort of get our hands on, actually, and we can be certain about those things. This is a wonderful self-portrait of Mach. It's called View from the Left Eye, okay? And you see, it's Mach sort of drawing himself, as from the point of view of what his left eye sees. And it's this kind of perception. Some things are seen clearly, some things not clearly. Some are close, some are far away. But it's this kind of perception, this kind of looking at the world that Mach thought we were doing when we were doing science. And of course, at the end of the 19th century, when people started talking about atoms, Mach thought that was absolute nonsense, right? Because we can't get at atoms. They don't have to. There's nothing to do. They don't relate to our sensory perceptions. And Lash-Miller agreed with him. Some of you will know that the chemistry building here is called the Lash-Miller building. It's named after Lash-Miller, who was chair of the department for a number of years, also commander of the British Empire. I have no idea what that means, but it was some sort of honorific title. Okay. He was, did important work in extending the work of, Gibbs on thermodynamics, but Miller really did not believe in atoms. This is documented in the official history of the University of Toronto. It says that in the book. Okay? Now I'm going to tell you a story that is not documented in this book, but I heard it from a former chair of the chemistry department. So I'm not saying it's true. I'm just telling you, I heard it from a former chair of the chemistry department. And it had to do with a visit that Ernst Rutherford made to the University of Toronto. He was spending some time at McGill University. Okay? And the physics department at U of T invited him to come down from McGill and give a talk on the stuff he was working on. Okay? And the stuff what he was working on was, scattering off of nuclei, right? And sort of understanding the kind of structure of the atom on the basis of the scattering. So the talk was, of course, full of atoms, okay? Full of the talk of atoms. And Miller sat in the back row. Okay? He brought with him a big box. Okay? And he sat in the back row. And then at the end of Rutherford's talk, there were questions and so on. And people asked various questions. And Rutherford answered. And then it sort of died down. There were no more questions. And then Miller raised his hand. Okay? And he was recognized. And he immediately went into a tirade about how it was nonsensical to talk about atoms. This was just ridiculous. It was unscientific. It was sort of mythology. This is not what science should be about. And he ended up saying, and here's what I think of your atoms. And in the box, he had brought a bunch of explosives and he lit them off. Okay. And there was a vast amount of noise and sound and confusion, smoke. The hall had to be cleared. And for years, chemists were not allowed to attend colloquia in the Department of Physics. Okay. Now, of course, with the discovery of Brownian motion and other scientific work, atoms, people began to take atoms seriously and so on. And of course, besides Brownian motion, sort of Einstein worked out the special theory of relativity, which also got rid of the absolute time that so much bothered Ernst Mach. Okay? But this led to a new kind of phenomenalism, a different kind of approach to the phenomenalist approach, to the phenomenalist program than the one that Mach took. And it was largely due to Percy Bridgman. And he was a physicist. He actually won the Nobel Prize in Physics in 1946. And what you can see there, the gadget on the left is a sort of high pressure device of the time in 1946, and the other ones are some samples that he had put in it. So he won the Nobel Prize for work he done on high pressure physics. Okay? And he was seriously bothered by, he appreciated the work that Einstein did, but he saw it sort of as a shock, because he said, we had missed everything, right? There was all this Newtonian time business, and we missed all this business that Einstein pointed out to us. And Bridgman wrote, it was perhaps excusable that a revolution in mental attitude should occur once, because after all, physics is a young science and physicists have been very busy. But it would certainly be a reproach if such a revolution should ever prove necessary again. So Bridgman wanted to avoid the kind of situation where we missed relativity for so long. And Bridgman thought we'd missed relativity for so long because we were hung up with these ideas of what time actually was and what space actually was, what was really going on. And we shouldn't bother about that if we want to do proper science, okay? Bridgman said every physical concept should be synonymous with a unique set of physical operations. So if we want to introduce a concept like space or a concept like time, we should really refer to that concept as the procedures that you might colloquially say we use to measure it. Okay? And this approach is called operationalism. Okay? And it falls in this phenomenalist category because here, science is about these experimental operations. So for example, if I want to talk about length, what is really length? The length of, a streetcar or something. I should say, well, I take a meter stick. The procedure is I take a meter stick, I go to the back of the streetcar, I put the meter stick down, and da-da. And the number I get is the length of the streetcar. Now, of course, if the streetcar is going by at a fraction of the speed of light, I have to do a different experiment and I will get a different number. Okay? But Bridgman thought that was okay. We then learn that there are these two different lengths, not just one. Okay? And we would never run into the kind of confusion that we would get into if we assume there was some fundamental, deep, sort of principle talking about what is length and what is time. And this approach is what dominates essentially all modern work on quantum information processing, quantum communication, efforts to build quantum computers, and so on. Right? Quantum mechanics is seen in this sort of way. Okay? There are gadgets that do preparations. That's what the big P is, and you see there's a little dial there so one can select which preparation you want, and so on. And there's a button you press that starts the experiment. Now it looks like there's a little port there, and it looks like something might come out of that port and go into the next box, but don't look at that. That's not part of the real story here. Next box is a transformation, and you can adjust the dial there to implement whatever transformation you want. And next box is a measurement gadget, and it's going to spit out a number. That's what the pointer dial there is. And in elementary quantum mechanics, preparations are talked about, are described by Ketz or wave functions, transformations by unitary transformations, and measurements by Hermitian operators. So we would normally, you might say that, we prepare, you might say that we're going to prepare the system in a particular way, but you don't do that here. You just say there's a preparation. Okay, it's not a preparation of length, for example. It's a length preparation. It becomes an adjective. It's just a kind of preparation. And likewise for the other processes. Nowadays, when there's more sophisticated developments where we talk about preparations in terms of density operators, transformations in terms of trace preserving completely positive linear maps, okay, and measurements in terms of positive operator value measures, okay? But it's the same idea, okay? One takes these, one's describing these tasks in the laboratory, okay? And of course, you can do more complicated things. After a measurement, you can do other transformations and other measurements, and so on, okay? Now, an important building up point of quantum mechanics. Okay? From classical special relativity, we learn something. Okay? We learn about something called signal locality, which just means that you can't send signals faster than the speed of light. Okay? That's a result of classical special relativity. So in the picture here, it means that if I take these two regions, RT and R prime and T prime, some of you will know that these are space-like separated, but you see they're at the same time and they're some distance apart. So you couldn't send a signal from one of them to the other because they're, say, at the same time and you had some distance apart. That signal would have to go much faster than the speed of light. Okay? So what you do in quantum mechanics, again, for the experts, is if you take field operators in one region and field operators in the other region, and if they're space-like separated, then you set the commutator of those equal to 0. If you don't know this, don't worry about it. It's just a technical way in doing quantum mechanics where you can guarantee that signal locality is in the theory. So signal locality is not a consequence of relativistic quantum mechanics. We build it in to relativistic quantum mechanics. But we build it into relativistic quantum mechanics because we find it gives a good description of our world. Okay? So with all of this approach, sort of the operationalist is sort of triumphant. Everything is working out very well for the operationalist. Okay? But the realist is a little unhappy with the situation. Okay? Because, I mean, the operationalist might say, what, inside of atoms and so on, why, you can't, just stick to the operational formulation. You can't really see in there. You can't talk about what's going on in there. Yeah, and the realist says, well, look, I also can't talk about what's going on in the center of the earth. Okay? But we have theories and we write down things about cores and mantles and so on. And it's true that we can do experiments on this part of the universe that we have no direct contact with. Nature does the experiments for us. There are earthquakes, and one can look at the waves that get propagated. One can sense those waves and so on. Those are the experiments. But the realist says, look, I can do that, but you mean to tell me that I really can't think about what's going on inside the earth, that I should just focus on, what the gadgets are telling me when I get an earthquake? I certainly know of no geophysicist who would take that operationalist point of view. Any geophysicist is going to say, of course, there is a core. Of course, there is a mantle. Okay? They firmly believe that you can talk about what's really going on in the center of the Earth. Maybe it's hard, but you can really do it. Well, if you can do it for the center of the Earth, why can't you do it for the center of an atom? It might be difficult, but we should be able to do it. Okay? Right. So, well, the realist might look at this situation here and say, okay, well, maybe the problem is that these probabilities are not the whole story. There's really a deeper story that's going on. There's some variables there that we don't know about that would tell us, exactly where the particle would be. So these have, in the field, these are sometimes called hidden variables. And, maybe if we could find those hidden variables, we could build a realist story of quantum mechanics. Okay? There's a problem with this approach that was pointed out by John Bell. Okay? And Bell considered the following situation. Let's look at these two space-like separated regions that I talked about. But maybe the observer there sends out two particles, one into region 1 and one into region 2. Okay? And those two particles are sent out in a very strange state. It's called an entangled state. Here it is for the people who have seen this before. If you haven't, don't worry about it. The point is that it's not a simple state for particle 1 and a simple state for particle 2. It's a state that sort of has particle 1 and particle 2 entangled. Okay, they're sort of messed up with each other in that state. But still, particle 1 goes over here, particle 2 goes over here. Now, let's suppose we make a measurement on particle 1. In the actual system that I'm considering here, these are two spins that are going off. So you can measure spin up or spin down in different directions. But let's not worry about the details. Let's just say you can make a measurement here and you will get a certain result. And then I make a measurement here and I also get a certain result. Sometimes I make a measurement here, I get this result. Well, maybe over here, sometimes I'll get this result, sometimes this, sometimes this, sometimes this. Maybe they'll be different. Okay? There'll be a range of results. But I can look at the correlations between these, okay, and see how the results I get in region 1 are related to the results that would be got in region 2. Okay. Now, what you find is that you can only understand those correlations if there is some kind of superluminal, faster than the speed of light, some kind of superluminal interaction between the hidden variables in those two different regions. There has to be some interaction that goes faster than the speed of light. Well, what do I say about that? Well, you might say, okay, maybe that's the way it is. I mean, after all, relativity is sort of a macroscopic theory, if you think about it. How do we introduce relativity? We talk about rods and clocks and things. These are macroscopic, big things. Maybe things are different at the microscopic level. Okay? But the problem is that signal locality is built into relativistic quantum mechanics. And it agrees well with experiment. Relativistic quantum mechanics predicts antiparticles and so on and so on. A whole host of stuff that is, really in agreement with experiment. So we know that despite these non-local correlations, we somehow cannot use them to send a signal from region 1 to region 2. Okay? We can't communicate using these interactions that are going faster than the speed of light, but the very theory that tells us they're necessary tells us we cannot use them to communicate. We can't use them to send a signal. Now that smells like conspiracy. Okay. So either the universe is really, holds a pretty low opinion of us and is trying to, screw around with our minds, right? Or maybe something's very fishy here. Maybe the realist approach, at least when we get to the quantum level, just doesn't make sense. Well, you can ask about other strategies besides phenomenalism. There's something called pragmatism that I want to mention, okay? And in pragmatism, it just basically says that, science is about nothing, okay? This is William James, the American philosopher, was one of the first people pushing this point of view. He wrote, he was quoting a colleague of his, actually, and he wrote, "I think that the sickliest notion of physics, even if a student gets it, is that it is the science of masses, molecules, and the ether. And I think that the healthiest notion, even if a student does not wholly get it, is that physics is the science of the ways of taking hold of bodies and pushing them. Okay? It's getting jobs done. And as long as the formalism is consistent enough that we know how to use it to get jobs done, to build quantum computers, to build semiconductor gadgetry, and quantum mechanics is, we know how to deal with it, we should be happy campers. Okay? A sort of modern pragmatist is Arthur Fine, who writes, "What binds realism and anti-realism together is this. They see science as a set of practices in need of an interpretation, and they see themselves as providing just the right interpretation." But then he says, as we grow up, I think we learn that such questions really do not require an answer, but rather they call for an empathetic analysis to get at the cognitive and temperamental sources of the question, and then a program of therapy to help change all that. So for those of you who are concerned about these kinds of issues and worry about what science is really about, all I can recommend is you go over to Student Services and arrange for some therapy. So thanks very much for your attention. Right.
What is it?
Well, I think you would learn that if the different methods gave you different answers, then you know that there are different lengths. And you've learned that the assumption that those measurements are the same kind of measurement is wrong. And therefore, since physical quantities are associated with measurements, you introduce new physical quantities. So the measurement, the measurement sort of, as it were, is the length. You're not doing a measurement of the length. You're doing a kind of measurement that for maybe historical reasons we call a length measurement.
Let's say that when this car is moving.
Yeah.
What kind of event?
Well, because I could do two kinds of for the moving streetcar. I could do in the laboratory. I could round up a bunch of students and put them in a row and give each one a clock, and I could synchronize their clocks. Okay, and then I would, as the streetcar went by, I would have I would notice when two of these students one saw the front of the streetcar, one saw the back of the streetcar at the same time. And I would call that the lab length measurement. But I could also put a student inside the very same streetcar. And that student would put out the meter stick in the usual way, and he would get the usual number for the rest length of the streetcar. So we have two different length measurements. And there's no contradiction there, but we've learned that we have to be careful if we're talking about length measurements, which gadgetry we're talking about. Okay. Yeah. Right. So I mean, you would really have to talk to different pragmatists. Okay, so I don't want to speak for all pragmatists or any pragmatist really, but I think a pragmatist certainly wants to make sure that the formalism is consistent and there are rules for how to use it and so on, and that's all straightforward. But and then a pragmatist will want to expand science if one goes into new territory, and one has to, right? Because one has to get stuff done in some new scenarios or some new situations, right? So yeah.
At like measuring length. Only thing is the true method, the right way to do it. There have been views like that of Leibniz's view. Time is at all the time. And don't think argument. Don't believe that, then you're in the wrong. Give us theory that don't.
Well, and pragmatist is very, very loose about things, right? Anything will do. I mean, to be an operationalist, it means that when you believe that when you're really doing careful science, you should just talk about these tasks. Okay. Now, an operationalist is not going to disallow physicists having an imagination, right? The famous physicist Kramer, somebody just asked him, how do you think of an electron? And he said, as a little blue sphere. Now, Kramer didn't really believe that an electron was a little blue sphere. Okay, it just helped him think about it. Okay, and certainly operationalists can use whatever mental imagery they want. Okay, but they would say, well, when you're being careful, when you're writing scientific papers, when you're talking at a conference, you should carefully define things in terms of the tasks in the laboratory and the results you got.
Then they think that.
Yeah.
Well, I know there's a story. What is the reason? Is not going to be.
That's certainly one reason. Yeah, and for Bridgman, that was a large part of the story. Okay. Well, because if you're a pragmatist, roughly speaking, you want to make money off of it. Okay, you want to be able to use it in a useful way, which is not exactly what a realist or a phenomenalist is after. Right. Yeah. Uh-huh.
I feel like this. I don't think anyone theory is wrong in some yes not rather playing a part in the to actually be confident. Can do is that say that I messed up some part. The results should be
Right, but if you do the experiments I sketched out, you will get two different results. One is the proper length, and you know, one is of the streetcar, and one is the length of a moving streetcar. So those are whatever you think about it, wherever you sit in the spectrum, that you do those experiments, you're going to get two different results.
okay. What will prompt one?
Well, if you thought that there was only one concept of length or one meaning of length, then you would be puzzled by those two different results. And according to somebody like Bridgman, okay, if you were in a situation like that, you would learn that you had to reformulate your theory. So, you know, yeah, these when we talk about a kind of measurement, that's kind of you know, there's a that's refers to a sort of, you know, sort of class of gadgets and so on. And then you learn whether you've got that class of gadgets properly identified or not properly identified. Yeah.
We walked over like we have like a bell state.
Yeah. Mhm.
Would it impact like, absolute plastic communication?
Well, in the end, you have to, whatever you're doing, yes, you have to get together and you have to compare the data. But the point is that the correlations that you see cannot be understood unless there's some superluminal signaling between those two measurements. Okay, they can, and you know, they go out and they measure the correlations. They, you know, come back and have dinner together and, you know, sort of compare their data. They, you know, they can establish the correlations, but those Bell's work showed that those correlations can't exist in a kind of hidden variable model, okay, where there's an underlying reality, unless you have superluminal communication. And you see the strange thing, because if you just believe that, you say, well, okay, maybe there's superluminal communication. But we know that if you had superluminal communication, you would normally think that you could send signals faster than the speed of light, but you can't. And that, you know, that's conspiratorial. Well, I mean, they collect their data here and then they come back together. And if you know, if you're going to assume that it doesn't affect their notebooks or anything like that, then I think that's safe. Yeah. Yeah.
Do you think that all that science can explain?
Do I think that all that science can explain is physical? I'm not quite sure what you mean by physical. Well, that's what's okay. I'm still puzzled.
So, do you think that everything in science down to that?
Could you give me an example of what somebody might think couldn't be?
So maybe there are topics in psychology
Uh-huh.
that might not be able to down to that. Do you think that despite some of those views, just a lack of knowledge on our part, or do you think that there might actually be more to science than just atoms?
Ooh, well, science isn't atoms in the universe. Science is it's a process. It's an endeavor. It's something one does, right? So science is not an atom. Science is the business that scientists do. Okay, and that has some bearing that talks about atoms and makes statements about atoms and so on. Are you asking whether I think it could make statements about psychology? Or I mean, I think it can. I mean, I don't know. I'm not a psychologist, but there is a science of psychology. It has certainly had some successes. You can argue it's a young science, certainly younger than physics is, but I think it's had some remarkable successes in understanding human behavior. So I think science can deal with those issues as well as atoms and nuclei and quarks. I'm not sure I'm answering the question you're asking, but
if it's possible to reduce certain concepts of psychology down to fundamental ones and then build up everything from some fundamental assumptions. Is that
that's kind of what it is.
Oh, okay.
I think it's more emergence effects.
Okay. Well, those are the questions that Patrick talked about, right? I mean, there are issues there about whether you consider. I mean, nobody is suggesting that if you have a pet cat, that you understand that cat in terms of particle physics, right? Nobody's suggesting that, okay? Because there are these higher levels that one uses to understand things, and we use them all the time. Okay? Now, in many cases, one finds that one can reduce those higher level things to descriptions at a lower level. That doesn't mean that you don't get new physical phenomena. I mean, even in condensed, nothing as complicated as a cat. Let's just say we're doing condensed matter physics, okay? Where the fundamental, let's say we got nuclei, we got electrons, we can write down the Hamiltonian, okay? We know what it is. You can go in the lab and you can see phenomena that you can't link in any simple way with the properties in that Hamiltonian. Okay? But that doesn't mean that there's anything else besides that Hamiltonian there. Okay? It just means that the features of the entities in that fundamental theory are not linked in a simple way to the features we see at a higher macroscopic level. But again, in condensed matter physics, where we know the situation fairly well, there's nothing else, right? There's nothing else in between. We're not missing anything. So I guess maybe the question you're asking is when we move up beyond condensed matter physics, and I don't know, maybe move up to psychology or something like that, do we believe there's anything else that we're missing? And I'm not sure I have my hunch, but it's just a hunch because I've not worked in that field. My hunch is no, but that's a hunch.
Yeah. Sorry for the silly question, but what is your opinion on
Some of my best friends are chemists. I don't know. What do you want me to say? It's, again, there are concepts in chemistry that are very, useful, like a covalent bond. Okay, this is not a fundamental physical thing. Okay, but it's a concept that's very useful in understanding chemical processes. I have no objection to people talking about the properties of chemical bonds. I do it sometimes myself. Okay. So that's what it is. Okay. It's a science at roughly, at a little level up, one, macroscopic level up above physics. I don't think there's any magic between, covalent bonds and fundamental physical laws, or here I can say even the fundamental, non-relativistic Hamiltonians that work pretty well for most of chemistry, right? I don't think there's anything in between. But certainly there are chemical phenomena that are best explained and understood without worrying about wave functions of electrons, right? There's a higher level of description that one uses.
All right.
Okay? Is that okay? Yeah.
I have a question.
Uh-huh.
So as far as I understand, in a lot of quantum field theory and so on and so forth, you do is you have some classical notion of certain things, and then you say, okay, now this is an operator, and then do a bunch of math and make certain assumptions, and then you get some new results. Vaguely. But in that sense, aren't we still kind of hung up still on classical notions? And do you think that perhaps with this approach, that's kind of hindering us from maybe noticing something else?
Yeah, certainly we are hung up with classical notions. We all grew up in this world, in a classical world. And indeed, our species evolved mostly dealing with classical things. We didn't, our ancestors, sort of slightly beyond Neanderthal did not have to worry about doing things at CERN. Right? It was they had other concerns, and classical mechanics is pretty good for all those other concerns. So certainly we have a classical heritage that we bring to bear. I mean, I particularly like quantum optics, for example, because it's an area where you're always moving back and forth between the classical and the quantum. Okay? But you can look at aspects in quantum mechanics that go beyond our classical imagery. I mean, the simplest one might be a spin 1/2 particle and how we describe that, right? There's no underlying classical model for that, okay? But one learns how to build the algebra and the equations for a spin 1/2 particle and other kinds of particles, much more complicated ones, okay? And so one can go beyond that simple picture that we have in the classical regime to come up with new theories at the quantum level. But of course, it's hard. Anything new is hard. Yeah. Yeah.
Like, is there
Right.
is this like we know that it works?
Yeah. Yeah.
Should we maybe, if we're going under like could we be
Right. Okay. Well, first of all, there's a number of different kinds of quantization, right? Standard one, there's geometric quantization, there's path integral, and so on and so on, right? So there's a whole range of processes there, and one has to come up with some way to write down equations. Anything that works is fine. Okay. If you're asking, are we being held back because we're not clever enough to see new ways to write down equations? Almost assuredly, yes. Okay. But, intellectual progress is slow. Okay, I think. Okay, again, thanks very much.